My name is Ryan LoRusso. I'm a second-year graduate student from Indiana University Bloomington, and today I'm here to talk to you about the free-floating and wide-orbiting planets produced from breaking the chains of cold Neptunes. So from microlensing surveys and inferences from the observed population of microlensing planets, we expect that free-floating planets are common, 2 to 20 times more so than bound planets. The mass ratio distributions of planets detected through microlensing indicates that the planets of approximately Neptune mass and below should be among the most common detections. The work of Suzuki et al. Places the peak of the free-floating planet frequency distribution with respect to mass ratio at just above a Neptune mass. And one of the peaks of the double Gaussian fit of Zhang et al. 2025 is coincident with Neptune's mass as well. Given these expected distributions, we are moved to ask what drives this high number of free-floating planets of Neptune and sub-Neptune masses. For our part, we approach this question from a dynamical standpoint, which is how could these Neptunes be ejected from a planetary system? Since we approach this question from dynamics, we assume that the Neptunes are going to be scattered by some body after a close encounter. The expected outcome of close encounters between celestial bodies can be broadly predicted by the Safronov number, as was discussed yesterday. A body with a high Safronov number is likely to have ejections dominate its close encounters, whereas a body with a low Safronov number is a more effective collider, with collisions being the dominant outcome for close encounters. In principle, the most effective scatterer of planets would be a high-mass planet distant from its host star, so called Jupiter. But most planets orbit low-mass stars, and low-mass stars tend to lack cold Jupiters. So what about cold Neptunes? Low-mass stars can host multiple cold Neptunes, but they're far less effective scatterers of planets. So in essence, hello. Sorry, there we go. So in essence, this is a numbers game. There are few cold Jupiters, but they can easily eject Neptunes, whereas with many more cold Neptunes, only some fraction of them will be ejected. As you've kind of seen before, and I'm sorry this one doesn't go all the way up to a stellar mass. The sum major axis mass plot displays the demographics of exoplanets currently discovered through transits, radio velocities, direct imaging, and microlensing. Most of the discoveries are clustered around the largely transiting inner hot Jupiters and super Earths, well below a Safronov number. Oh, I have the pointer. Well below. Is this working? Oh, there we go. Well below a Safronov number of unity, and or around the cold Jupiters, which are well above a Safronov number of unity. The microlensing detections, on the other hand, tend to dip down towards Safronov number of unity at around a few Einstein radii. Because a significant sample of cold Jupiters has been detected through radial velocity measurements, we have some idea of cold Jupiter system architectures. However, the same cannot be said of cold Neptunes, whose planetary system architectures are largely unconstrained. To that end, we aim to infer the architecture of cold Neptunes through their short period analogs, as well as through our expectations given models of planetary migration. With respect to short period analogs, prototypically, we consider the Kepler compact multis. Many Kepler compact multiplanetary systems are in or near to a resonance. Young planetary systems exhibit a much higher incidence of resonance. That is, a much higher proportion of young systems are in resonance than in older systems, which tend to fall out of resonance. The uncertainties on the incidence of resonance among these young systems arises from small number statistics, whereas these older ones are better constrained. Planetary migration models indicate that resonances occur naturally during planet migration, provided that that migration is slow, low eccentricity, and convergent, as is the case with disk migration. The classic breaking the chains model of Isidoro et al. Is one compelling explanation for the dissipation of resonance in these Kepler compact multiplanet systems. In their model, disk migration captures planets into a resonance, specifically into resonance chains, where sequences of planets where each subsequent pair is in resonance. These resonances are slightly overpacked, meaning that when the disk dissipates, the resonances destabilize and the chain breaks. This is great for super Earths, but doesn't work quite so well for Neptunes, because Neptunes tend to capture into wider resonances further out in the system. They're harder to destabilize. Another clue as to the architecture and prevalence of cold Neptune systems comes from debris disks. Debris disks, and by extension planetesimals, are common, occurring frequently around young FGK-type stars and less common around older FGK-type stars. To leave it a discernible dust signature, they have to be dynamically perturbed, thus we have to invoke some kind of dynamical stirring. If cold Jupiters were the celestial body most responsible for the stirring producing visible debris disks, the prevalence of the disks would be difficult to explain. On the other hand, if Saturn's or Neptune-sized bodies were primarily responsible, their prevalence would not be. This begs the question as to whether there is a real example of a system with both a resonant chain of Neptunes as well as a significance debris disk. And if there is, what is the architecture of that system? There is such a system, to give a slight spoiler. It's AU microscopy, which is one of the systems in the Young Resonant Systems basket of Dye et al. It's a 22-year-old M1 star system with a multi-planet system. It contains 3 Neptune or smaller sized planets very near to a 3-2 resonant chain, and potentially a 4th planet itself, also Neptune-sized, exterior to the system, but hovering somewhat interior of the 2-to-1 resonance. Moreover, it's been suggested that the planets in this resonant chain are significantly misaligned, indicating a potentially dynamically active early history for the system. It also retains a substantial debris disk stretching from 35 to beyond 200 AU, and JWST imagery of the disk and the system is sufficient to rule out the presence of cold Jupiters within or near enough to perturb the disk. Correspondingly, the architecture of the system must be shaped only by Neptunes or smaller planets, at least from what we can see of the planets that remain. Our simulations aim to answer what such systems would look like, whether they can produce the requisite population of cold Neptunes so as to satisfy the observational criterion imposed by microlensing, and what other dynamical consequences may ensue. We set up a chain of 5 cold Neptunes captured via simulated disk migration into a 3-to-2 resonance chain about a 1 solar mass star, with the innermost Neptune at roughly 3 AU and the outermost at roughly 10 AU. That's it. After this migration, the Neptunes have low inclinations of less than a degree and low eccentricity. The configuration of 3-to-2 cold Neptunes is long-term stable after the disk dissipates, and unlike the Kepler multis, it does not chaotically destabilize after the removal of the disk, and correspondingly must be perturbed to do so. For that, we turn to the debris disks to provide our common perturbers, which are going to be planetesimals. A planetesimal can drive scattering between planets in a resonant chain. To simplify, consider a single pair of planets and a single planetesimal scatterer. This planetesimal scatterer jumps between curves of constant Jacobi integral, the net result of which is to drive a separation in period between a pair of planets. When such a pair of planets crosses a resonance from below, they get an additional kick in separation as well as an eccentricity. If we have a resonant chain of planets, if we kick one pair over the resonance, another pair will be kicked below it. And so you can get a series of repeated kicks that leads to a faster destabilization of the chain. Therefore, after the disk is removed, we instantiate planetesimals comprising in total a few percent of the total mass of the resonant chain of the 5 Neptunes. These planetesimals have comparable eccentricity and inclination to the Neptunes after the removal of the disk and are treated as full particles. In principle, we might also refer to these as planetary embryos. So here we have a diagram detailing a schematic simulation as conducted in Rebound using the Buehler-Storch integrator. The top panel consists of a side view of a typical system, the middle, the top-down view, and the bottom a caption describing the current stage of the simulation and the time it takes for the system to achieve a like state. Planetary orbits are given as colored ellipses, planetesimal orbits as gray ellipses, and the approximate planetary disk as a translucent gray torus. To begin with, we start our simulations with the 5 Neptunes embedded in the disk and just wide of the resonance, and let them capture into resonance over the course of 4 million years. We then remove the disk and add planetesimals to the system, and at this point, all bodies in the system are roughly coplanar. This will not last. The resonances in the system quickly dissipate as the planetesimals drive scattering, being broken on the order of 100,000 years or less. This on the right-hand side shows the resonant angle, which very quickly, the fluctuations in the resonant angle very quickly reach amplitudes covering the whole range, the full range of angles. Even in a broken configuration without perturbations by planetesimals, the cold Neptunes can remain stable for hundreds of years. Planetesimals in these systems are also largely lost early, with more than half of planetesimals being fully lost from the system by around the 10 million year mark or so. However, most planetesimals have already been scattered such that they are rather more wide orbiting than the chain of planets, with some number of infrequent perturbations. Even if the system appears to remain stable millions of years after all planetesimals are ejected or lost, the system can destabilize hundreds of millions of years after the initial perturbations. At this juncture, planets are, again, still largely coplanar, and the planetesimals have expanded to cover a much wider degree of eccentricities and inclinations. We parameterize instability in the system with the AMD, or angular momentum deficit. As you may recall from the first day's talks, it, broadly speaking, measures the excitation of planetary orbits and is conserved under secular evolution. The equation describing AMD is provided here on the right. And to begin with, the AMD is relatively constant until the resonance breaks, where it jumps up by about a factor of 3, continues roughly at a constant level before, as the planetesimals diffuse the angular momentum, the AMD rises with a timescale. The AMD rises to about the square root of the time of the simulation until the system destabilizes, at which point it jumps up by orders of magnitude. Once destabilization occurs, the eccentricity and inclination of the planets varies wildly until they reach a comparatively stable state. The timescale for destabilization depends primarily on the total mass of planetesimals in the system, as well as the quantity. We produce 8 ensembles of simulations for 3 different numbers of planetesimals, varying the granularity of the planetesimal scattering, and 3 different total masses of planetesimals as well. In this figure here, the semi-transparent symbols are individual simulations in a given suite, and each color or marker shape denotes a different number of planetesimals, and the masses of these the sum of the planetesimals as a fraction of the resonant chain mass separate these 8 suites on the right. The box and whiskers here displays the median, the 20th to 80th quantiles, and then the full range of the simulations with the whiskers. If it runs off the end of the plot, that means the system didn't destabilize at all after more than 1 billion years of evolution. As you might expect, the higher the mass, the faster the destabilization. There's also a secondary effect coming from the number of planetesimals, from the granularity, in that individual more massive planetesimals tend to also drive faster destabilizations. In the end, most but not all systems are left with 2 to 3 long-term stable but eccentric planets, often which are evolving secularly. The fate of the remaining planets initially in the system is one of 3: collision with other planets, ejection from the system, or tidal disruption or capture about if the planet should approach too close to the star. Because the initial Safronov number for these planets is approximately 1 to 4, we have mixed outcomes. So there's a prevalence of both collisions and ejections, though it's slightly weighted towards scatterings here, which we take to be both disruptions and ejections. And you may notice that there is quite a high number of disruptions per system, at about 0.7 disruptions per system, which is about 2 to 3 times the disruption or capture rate of Jupiter's. And we think this is because the disruption fraction, given the Safronov number for planets at this orbital distance, is peaked at around, because the Safronov number is very close to unity at around this semi-major axis for these Neptunes, we think that the disruption fraction is peaked at around the Neptune mass. We have some simulations that seem to show this is the case, but our work on this is ongoing. Additionally, we get a roughly similar amount of ejections, also at about 0.7 per system. That was two slides ahead. Relevant to the free-floating predictions, we find significant mass segregation in our simulations. Our leftover bound Neptunes are split into 2 populations, one of near constant semi-major axis and rising eccentricities from the initial conditions of the system. That corresponds to the higher mass planets near minimum energy, and one of rising semi-major axes and rising eccentricities that corresponds to the lower mass planets that tend to be much wider orbiting. These demarcations align quite nicely with detection possibilities for cold Neptunes through microlensing. The higher mass population aligns with populations of Neptunes detectable as microlensing. At a few Einstein radii, they're still discernibly bound to their host star. On the other hand, the wide orbiting population of lower mass cold Neptunes are at tens of Einstein radii and correspondingly may not be detected as bound to their host star. Lumping these presumed free-floating detections alongside the ejected population, we find the combination of the 2 is sufficient to be consistent with free-floating planet predictions. Overall, few systems remain in their initial resonant configuration, separating from their initial range of semi-major axes. This on the right is a roughly representative sample of the planets left after 1 billion years, where I've selected the kinds of systems that our simulations produce, with individual planets sized by the mass appearing as points on the lines representing individual systems. This green band indicates the initial range of the semi-major axes of these planets. Higher mass planets crowd the initial range and below, whereas the lower mass planets are produced to far higher separations with period ratios between 1 and 250. Many of the synthetic systems in the sample contain wide-orbiting Neptunes, and some of them contain only wide-orbiting Neptunes. There's about 2 in the sample of 26 systems. Extending the planetary orbits this distance requires some additional energy to be added to the system. This happens because the energy of these outer planets is transferred to an inner planet whose eccentricity is driven up and eventually lost. Because of this removal, it adds energy to the system, and it leaves the new innermost planet at about tens of AU. There's a marked difference in eccentricity and inclination between wide-orbiting and disrupted planets, but I'm going to go ahead because I have only a little bit of time left. Systems containing these wide-orbiting Neptunes can be long-term stable. Prototypically, this is because they drive these outer Neptunes drive secular changes on the inner planet's orbit and eventually cause this inner planet to get disrupted. In theory, this should leave some sort of observational signature in inner systems, and we've run a couple of simulations that show that it should destabilize inner resonant chains if systems have them. Overall, we find that about half of bound planets have a wide orbit with a projected separation of greater than 20 astronomical units, and that the planets on these wide orbits account for about half of the planets that would be detected as free-floating planets of the Neptunes ejected by our simulations. Obviously, this is on the low end of the observed free-floating to bound ratio, but it's also all Neptune mass planets, as opposed to the much smaller planets that would be ejected through a pebble accretion method, like the planetesimals, which are almost exclusively ejected. Yeah, I have next steps, but I'm out of time, so I'll open the floor to questions.
Thank you. Great talk. I'm not quite sure I understand how these, planets and resonant chain could actually form in that change, because presumably, so you get very high velocity dispersions for your planetesimals since they're being ejected, and so if you looked at the collision timescale for planetesimals, used to build these planets, they would probably be very short, and you would fragment them into dust. So, how do you deal with that?
So if I understand your question correctly, it's about the timescales for producing these planets within the disk, or for the planetesimals in the...
Well, you're arguing that this system develops a very high eccentricity, at least for planetesimals, and then planetesimals can be ejected as well. But wouldn't that imply very short collision timescale for your planetesimals? At very high velocity, so you would fragment them rather than grow planets from them. So
you're saying after the Neptunes are introduced, we have the planetesimals. The planetesimals are ejected very quickly.
How did you form the Neptunes in the first place? Because you need to start from the planetesimals, right? But then growing the Neptunes there gives you very high velocity dispersion in the planetesimal population, right?
Yeah, I'm not sure that I can totally answer your question. But for the initial setup with the Neptunes in the disk, we expect that the planetesimals in the disk will have substantial eccentricity dampening from the disk. And so in theory, they should be able to produce planets by co-accretion. I'm not sure that's a good answer to your question, but yeah, no. We've not looked extensively at the planet formation.
Yeah, I want to build on Sergey's question. I was going to ask same thing, but a little bit differently. You need those objects to form the planets, but what provides so much? My question is, what provides so much planetesimal after formation that facilitates that scattering? You got to have a huge amount of planetesimals after you have your 5 Neptune planets have formed through the disk of planetesimals. You must have so much of it left that does what you want to do. So my question is, where did they come from?
In theory, we only need a few % of the mass of the resonant chain. I agree that it's a lot, but Yeah, we've not done planet. I guess my answer to these questions is we haven't done planet formation simulations to actually assess the validity of these.
Let's talk about that.
Sounds like a good conversation to have at coffee breaks. So we're gonna stop here so we can move on to our next talk.
Yes.
Great job, Ryan. Applause for Ryan. Indiana University grad student.